All right. So
I just have Netflix now, so I don't need to.
the beginning part of this unit and the things we talked about with time dilation, length contraction, those were all part of Einstein's theory of special relativity. And it was special because it only related to things moving at a constant velocity. Now we talked about inertial frames of reference and how that affects the speed of light, blah, blah, blah. It doesn't affect the speed of light, but it does affect our perception of space and time, or distance and time. But Einstein realized that his theory was not complete. It was a theory of special relativity, the special part being that it only applied to constant velocity. But the universe doesn't work solely in constant velocities. The universe has acceleration. So he knew that if he had to redefine the universe and how we were supposed to perceive it, he would have to figure out acceleration. All right? So, Austin, to use your phone as an example, right? You know, phone gets knocked out of your hands or knocked off the bathroom counter. I don't know what happened, whatever.
I was coughing and my arm hit the counter and it fell off.
Yeah, so, okay. But then...
It's almost as bad as Bush choking on a pretzel and, like, getting...
Easy. He was sick and he was coughing. Come on. That was so
Yeah, that's microaggressive.
So, but, so we let the ball go and it goes to the floor because of gravity. But what Einstein said was, let's consider you were in a room like this one. And there were no windows or doors. You couldn't see the outside. If you let this ball go, it would fall to the ground at an acceleration of 9.81 meters per second because of gravity. But let's say, in a different situation, gravity didn't exist. There was no such thing as gravity. But this room was accelerating upward at a rate of 9.81 meters per second squared. If you let the ball go, what would it do?
Stay.
It would stay, because inertia tells it to stay. But if the room is accelerating upward at 9.81 meters per second, eventually where would it end up? On the ground, or at least what you perceive to be the ground, right? Because the ground is down there, but now it's up here. But the gist being, would it look any different? Yeah, because the floor would give it a force. Right. Well, if the force was big enough to stop the acceleration, or to stop the downward velocity and start it back accelerating in the upward direction again, then yeah, right? It's the same thing between that or if we drop a lump of clay, right? Because of the nature of the ball and the nature of the clay, here, because the ball squishes as the floor applies a force to it, it applies a force back to the floor, but because of the squishing, it applies a force for a longer time. Does that make sense? And so that's why it ends up going back up. But the clay doesn't have that bounce back, so the floor doesn't provide enough force to push it back up off the floor. Yep. But no, because let's say we threw it at 15 meters per second upward, okay? Well, no. Once it leaves your hand, Joe, right, what will it continue doing? Keep going in that direction, 15 meters per second upward. But what is the room doing? It's not going 9.81, it's accelerating 9.81. So as soon as the ball leaves your hand, it continues to go 15 meters per second in the upward direction, but the room is steadily gaining speed in the upward direction. So eventually what would happen? because the floor would continue to gain speed faster, faster, faster. So when you first let the ball go, it would be going faster than the floor, so it looks like it goes away from it, but then the floor gains speed and catches up to it. Does that make sense? So, same thing. So what Einstein says is that you can't tell the difference between gravity, or what we call gravity, and an accelerating frame of reference. And like we discussed yesterday, if the floor, the room wasn't accelerating, and we let this ball go, what would it do? It would just stay there. It wouldn't get any closer or farther from the floor or the ceiling, because the floor, the ball, and the ceiling are all going the same speed in the upward direction, and then it would look like there was no gravity. Right?
If there's no gravity and you let the ball go, hypothetically, wouldn't it move somewhere just because of the small little differences?
Technically, yes, right? But it wouldn't fall to the ground. You know what I'm saying?
It would like go somewhere.
Yeah, like now, I suppose in theory, if I let it go at just the right time, left and right, then it wouldn't go anywhere because those two forces would cancel.
But most of the time, wouldn't it just kind of like, because there'd be small differences in the forces.
Yeah,
Small
right.
differences make
Now,
it-
if the difference is so small on one side or the other, it might start accelerating one way, but it would be a very small
it's kind of
acceleration.
a little bit.
Right, you know. But that's also, Austin, that's actually something that working in a space environment, you have to be somewhat careful about that, because if you go, like, you know, if you're a spacewalk, right, you know, astronauts out there in space, if they go to move, they push off of this to go that way, right? But if you don't push right, you can start yourself spinning. You know, if you push, you start yourself spinning, and there's like
There's nothing stopping.
there's nothing
you.
stopping
Keep on
you,
going.
right? Yeah. So that's also when we talked about free fall. We talked about did we talk about Felix Baumgartner, the guy who did skydive from space?
I think so.
No.
Yeah, we did.
I,
So anyway.
It's not as space yet, right? It's like almost.
What does he have to do with it?
In terms of that definition, right? Like one of the things that actually happened in his skydive. So he went to 128,000 feet, which is like, quick math, about 5 times higher than a plane flies, and basically did a skydive, right? What happened is that, so for the first couple minutes of falling, he's out of the atmosphere. And so if there's nothing to, skydivers use the air to like push, basically, that they can steer themselves, because they can use the air on this side to push more than this side, so if they need to turn or flip or whatever, you know, like those people that do those crazy things in the air where there's like 27 of them and they make a big star, and you know what I'm talking about? Yeah, like synchronized skydiving, basically, right? They use the air to direct and push and things like that. But above the atmosphere, there is no air. So if you start spinning, you're just going to keep spinning because there's nothing to stop you. And one of the things that can happen, and this happens, Felix experienced this, but it also can happen with spaceships as they're coming into the atmosphere. If you come in at the wrong angle, the atmosphere will push you and basically like flip you. Does that make sense? Because you encounter that force, and if you're already spinning and then another force hits you the wrong way, it makes you spin even more. Now you can like black yourself out. Like that's actually he almost blacked out like on his skydive from space. That he started spinning so fast that he almost like blacked himself out. So yeah, that wouldn't be gravity though, right? That would be your little touches. So what Einstein then said was, okay, so let's do this. If I took a light, right? In essence, yes, right? If I shine the light across the room, as soon as it leaves my flashlight, it travels in a straight line. But if the room is accelerating upward, it wouldn't hit the wall directly across from where I shine it. And we talked about, like, okay, that kind of makes sense. But if you go back to this, where Einstein says you can't tell the difference between acceleration and gravity, here you can't tell the difference between acceleration and gravity. So that this should happen not just in an elevator that is accelerating in the upward direction, it should also happen if light is under the influence of gravity. And we refer to this idea as the principle of equivalence. That the principle of equivalence states that a physical experiment conducted in a uniform gravitational field and in an accelerated frame of reference gives identical results. And the end result of that is, like it says in orange right there, it doesn't say in orange on your sheet, but the principle of equivalence implies that gravity bends light. Okay? Good? Alright. It's one thing to say it, it's another thing to prove it. But for Einstein, Einstein doesn't prove anything. He just says stuff, and other people prove it. Okay?
Oh, why can't he just like prove it himself? Like,
Well,
he got like the
in his,
evidence.
so I think a lot of it is Einstein. In this, I'm just kind of speculating on Einstein's character, right? Because I don't know Einstein. He's been dead for 60 years, right?
I think like someone like that could die. It's just weird.
But I think a lot of it was just like, and I don't want to call it arrogance necessarily. I think he was just like, yeah,
He's those really chill people.
it's right.
Yeah, I watched this like that.
Yeah, like, no, it's here. I did the math. Here you go. It's right. Yeah. If you were like, wait a second,
Yeah.
just because you're right on, But when the more and more and more we test it,
He's right.
it's right. So, anyway, so what does this imply? Well, it implies that gravity bends light. Again, it's one thing to say it, it's another thing to show it. Alright? So, here's a picture that illustrates what Einstein is saying. Okay? In our solar system, the biggest source of gravity is the sun. And so, when we look at the sky, any light coming from a star behind the sun is affected by the sun's gravity. Okay? So, here, here is a star. That's the actual position of the star. And it sends out light. But when that light gets by the sun's gravity bends it as it's going around the corner before it gets to us. Our eyes aren't trained enough to determine if light is being bent along the way or not. Right? For example, if I look in that glass, right, I can see a reflection of some of you. I know it's a reflection because I can see you and I see the reflection and I know how glass works, alright? But if there was something like a wall right here where I couldn't see you guys and I didn't know the physical yous were sitting there, or if we were in Pittsburgh, I'd say the physical yins were sitting there, right? What? Say again? Yeah. Okay. If Horat was teaching this lesson, if he didn't know Yins was sitting there, right? Well, that's what
No,
people in
but he
Pittsburgh say.
doesn't.
You know.
He says,
He doesn't pronounce H.
Wow.
he says somewhat like
Yeah. But as far as our eyes are concerned, if I see a reflection of you in that mirror or in that window, if I didn't know you were sitting there, my eyes would go, oh, there's Cindy, there's Ben.
But won't
Right.
you like think that like why is it there? And it's like
Well, if, like I said, if I didn't know that
I know, but you can assume that you see a reflection. It's kind of like a mirror when you're like you don't, like when you're driving, you see a reflection of the car behind you. You don't see the car, but you see it, the reflection, so you know it's
But
there.
does your, well, you know that because you're trained to, like, you're trained to do that, right? But, like, so, if you go to a haunted house or a fun house or something at an amusement park, right? If there's a mirror at the end of the hallway, maybe it's like tilted sideways like this, right? So, if you're walking down a dark hallway, okay?
Oh my god, I hate those tower ones.
Right? And let's say there's a mirror right here,
Okay.
and a scary goblin-y,
Oh, you don't know if
right?
the scary goblin is over there or
Right.
is on the
Right,
mirror.
if you're here, right, and you see the scary goblin here,
Yeah.
if you don't know the scary goblin is down the
Oh,
hallway,
you're gonna assume that it's over there.
right. So that's what happens with our eyes. We're like, oh, the star is at, oh, we look up at the sky, and we're like, oh, the star is here. No, it's not. It's really over here. But the light going around the sun bends it, or the sun bends the light. So, you have to, now, this only happens, though, during the day, right? At night, when the sun is behind us, we see the stars where they are, okay? And so, half of the year, we see certain stars behind the sun, and certain stars not behind the sun, and then the other half of the year, when Earth, trucks it around to this side, we see these stars where they actually are. Does that make sense? Okay? So, here's what people did. In 1919, there was a very complete solar eclipse. Okay? Here, I'll show you a picture.
What year was it?
1919.
1919.
Aren't you like not allowed to look at those?
Well, you can look at them if you have the right equipment.
Why can't
You
the
should.
Total solar eclipse is more like.
Total solar eclipse, you can look at it for a little while. I mean, you got to be careful with it.
What if you stare at like a half solar eclipse with your eyes and just kind of keep looking?
You'll hurt your eyes.
Won't you? Well, they say you go blind, but do you go blind instantly?
No, I mean, very few things happen instantly here on Earth. Alright, so... Okay. So, back in, we said 1919, there was a solar eclipse that went across, and this is South America right here, and then went across Africa. Okay? So what scientists did was they took a picture of the night sky.
Wait, what's solar eclipse? Wait,
A solar eclipse is
was
when
on the moon?
when the moon is between the sun and the earth, so it looks like nighttime. Right? If you're in the path like that green line right
so
there,
you can't
it would
see.
look like nighttime in the middle of the day.
Okay.
Right? If it was a total solar eclipse.
Alright.
Right? We have several partial solar eclipses where the sun it's a little
So
bit
it only
light.
blocks the center and like the
Yeah,
the
right. So this here is like the total darkness. So scientists take a picture of the sky.
Wait a minute, there's no light at all.
It looks like nighttime,
Okay.
right? Because if you're.
But there is light.
There is, yeah,
Yeah.
right. Yeah. But I mean, dark enough though that you can see the sky. That you can see the stars. The
Okay.
stars are there in the daytime. We just can't see them, right? Because the sun's
Yeah.
light blocks
Yeah.
it out. So, scientists take a picture of the sky during the solar eclipse. And then, 6 months later, when the sun isn't between us and those stars anymore, right?
They compared it?
They took another picture of the sky. And guess what?
It's different.
It's different. The stars are in different places because during the solar eclipse, they had to go around the sun, or the light from those stars went around the sun. And they are displaced basically by the amount Einstein said they would be because they travel around the sun.
Oh my god, look at him.
And if you look at pictures of the sky, we take pictures of the sky from space, right, our atmosphere really makes things look bright. It scatters all the light, right? That's why we have daytime. In space, when you're outside of the atmosphere, you can see the sun, but it looks just like a really, really bright star. It doesn't totally dominate the horizon and the atmosphere like it does here on Earth because of the because you know, does that make sense? Right? So if you take pictures of the sun from space, you can see, and you guys can see this in your picture, and I'll zoom in a little bit so we can kind of show it. Notice as the sun moves across the sky, there's like this little halo around it where no stars show up. Well, kind of.
Why is that?
Because as the light goes around the sun, right? So Cindy, like we talked about, you know,
Yeah,
as the light goes around the sun, we see the stars this way as opposed to where they actually are. Does that make sense? Because this star right here is actually over here.
Oh, we just don't see it because it bends.
Right, because it goes around the sun.
Okay, yeah.
So yeah, when the sun isn't there, it appears in one spot, but when the sun comes across, because of the way that the light from this star bends around the sun, we see it over there.
Yeah.
And that happens on both sides of the sun. So you can kind of see in these pictures, right, that it said as the sun moves across the sky, that little halo like follows it, right? Here, this, right? There's no stars in that area right there because this star, right, is actually over here, but because of the way that it bends when it goes around the sun, it doesn't look like anything's there, right? Same thing if we go back to the first picture over here on this side, right? There's this halo around the sun where there's no stars, or there appears to be no stars.
So any star that's like behind the halo area would be sent, the light would be sent in a different direction that we're not looking from.
Right.
So it appears like there's nothing in it.
Correct. Because all those, like I said, all those stars on like do this, you know, and so all of the stars that we see close to the sun appear to be here and here because the light has bent as it's gone around the sun. Does that make sense? There's like that cone where there doesn't appear to be anything because all those light is going around the side. It would be like going back to the mirror thing, right? If you had a mirror in front of you that was kind of tilted. All right. So if this is you, and this is, let's say, like a triangular mirror, right? You would see things coming from here and here, but there would be nothing like right here. Does that make sense?
Yeah.
Right? And that's basically what's happening with the sun.
How come the sun bends light? Did you explain that before?
Because sun,
I know because gravity.
the sun has gravity, and gravity bends light.
I don't. Shouldn't it bend it towards the light?
Yes. So let's talk about why. Okay. So these things are happening. Oh, one more thing. This is kind of a famous thing. So this here is a picture of a famous astronomical event called the Einstein Cross. Okay? It was named after him. He didn't see it. Okay? So this right here, in yellow, this is a distant, bright, like supernova or galaxy that gives off a lot of light. Okay?
That's what we saw today.
Say again?
What we saw today.
We see this whole image through the telescope.
Okay.
Yeah, this is how it comes to us. So this is a distant, bright galaxy. but so is this, and so is this, and so is this.
What's in the middle?
But the weird part, hold on. The weird part is that all 4 of those yellow circles are exactly the same object.
Is it taken in different time intervals?
No. So if you look at this picture over here,
He's so scared.
okay, here is the distant object. That's the yellow
Oh
circle.
no, let's put it back.
That's the yellow circle that we see in this picture. But there's a bunch of gravity in the way. A bunch of galaxy, oops, sorry, shouldn't do that. Okay? This is what we call a galaxy cluster. And that's what this is in the picture. Okay? So purple and purple are the same thing. As light from this distant bright object goes past that galaxy, it bends around it, and you can see, right, that galaxy, this distant one, appears to be in 2 places at the same time.
And those two is up and down.
But the other 2 are up and down. So we see the same object in 4 different places
Oh god, that's scary.
because of the way that the light bends around heavy things. Go ahead.
Why doesn't it bend all the way around?
It probably does. It's just a matter of where, like, I see what you're saying, like, why doesn't it look like a circle? I can't answer that question, honestly. That's a good question, because, yeah, if it's coming from all places, it should. I don't know. That might be a good
There's a
thing
huge
to look into,
supernova.
so. Say again?
Why is there wait, there's a huge supernova that close to Earth?
No, no, no. This is like, here, look.
Oh, far, far away.
Yeah. Is it not in this picture? Oh, here it is.
But that is so cool. That just like proved him right entirely.
So, 400 million light years.
Oh, okay.
Yeah. Right. Again, that's light traveling at 186,000 miles per second for 400 million years. But the light is so bright that we see it.
How about that first picture? What is it?
The first, it's the same thing. That this is, these 2 things are the same object. Okay? We see them in 2 different places because we refer to this phenomenon as gravitational lensing because it bends the light as it goes around those galaxies. So, okay. I'm good.
So, if you think 400 million light years,
Yep.
do you ever think that if we can go to the speed of light, that someone would be able to survive that long?
See, I mean, even going the speed of light, it would take us
That's a long time.
400 million years to get there.
Oh.
Because
What if you were?
400
That's
million
so
light
sad.
years
That's
is
just
how
like
long light
impossible.
travels in 400 million years. Light year is a distance, right? Like, you know. So yeah, even going at the speed of light, it would still take it. But the other thing too is that we see these galaxies, and this is kind of like, you know, we see those galaxies, those four representations of the same galaxy, and we see it, we're like, oh, that's awesome. But it happened 400 million years ago. Like, what does it look like now? I don't know. We'll find out in another 400 million years.
It's not like it's like the stars, the closest star besides the sun's like what, 4.3 light years?
Yeah, 4.3 light years away. So yeah, we see it as it was 4.3 years ago. You know? So yeah, that's something to think about. It's like, oh, we see all these cool things in the sky, but it's like, wait a minute, that's how it was 400 million years ago.
And how can they tell?
We can tell, do you understand the concept of parallax? Okay, so that's
What's
cool.
tadpole?
So,
What
what?
do you ask? Some tadpole?
How do we know how far away it is? I appreciate your honesty. So,
No, I seriously, I don't know either.
I'm
all right,
genuine there.
so sun, Earth. Okay. Sun and Earth, right? Okay. When we look at stuff in the sky, we see it in different places at different times of year, regardless of whether the sun is there or not, right? So if this is a star we're looking at this time of year, we see it over here, but at this time of year, we see it over here, okay? Because of our vantage point of how we look at it, right? The closer things are to us,
Oh, we see it in
the more
different-
their apparent position changes. Because we look at them, because our vantage point, we look at them from deeper angles. The farther and farther away something is, the less its apparent position changes. So because of that, how much it shifts in our view of the sky, we basically make a triangle, and we know the base of the triangle, and we can figure out the height of the triangle based on where that position changes in the sky. Does that make sense? And then we just do base times height divided by 2, basically, you know? So that's how we figure out, well, that would be the area, but that's how we can figure out how far away things are, approximately at least. So, yeah.
So, like, in like the sense of like aliens, we really don't know if there's any aliens because they're seeing us, we're seeing them from 400 million
Right.
years ago.
Right.
But that's the same for us. So how
Yeah.
old, when was Earth built? Like how many years ago?
Actual Earth, like the planet itself,
Yeah.
is about 4.6 billion years old.
So, 400 million years ago, what would they be theoretically seeing?
They'd see a big, like, it would look like a big ball of magma. Because that's what the Earth, that's geologically, that's what the Earth was like in the early days, right?
400
Very,
million years ago?
And then
yeah,
it hit
like
puberty.
billions of years ago, right? No life. Life doesn't come around until way, way, way after that.
Like,
Because
what is life?
Oh, that's like bio.
I want to
What
say
about
a
bio?
billion years ago, but I'm not 100% sure on
You
that.
have to wait till
Well,
oxygen
400
and
million
nitrogen
is
goes to
different
sex.
than 1 billion.
Right.
So, what
But
were we doing
the
at 400?
dinosaurs, like the dinosaurs, were 65 million years ago. So that Einstein cross happened 335 million years before the dinosaurs were on Earth.
It's crazy
You know what
to
I'm
think
saying?
about.
Does that make sense? Right. So yeah, it's like, yeah.
So, that's why we haven't gotten any, like calls because they don't
Right.
know,
Right.
areas.
So,
What can they
well,
send a
or
call?
maybe now, okay, there has to be something like, but in that case, okay, light is coming off the Earth, great, okay, but that doesn't prove anything's intelligent there. We get light from stars all the time. It doesn't mean that there's any intelligence there. Have you ever seen the movie Contact before? Okay, it's a Carl Sagan book about some astronomers that receive a message from aliens. All right, but the way that they like get the signal. So this is a work of fiction, but it's based on science. It's based on science because Carl Sagan wrote it, and he's like, so. Anyway, the signal that they receive actually has pictures of Hitler. Like the alien signal has like pictures and video of Hitler in it, and the scientists are like, what the, you know, like why are they sending us pictures of this fascist dictator?
And they're gonna say something else.
And then they realize that the Berlin Olympics in 1936 were one of the first worldwide television broadcasts. So that signal
Just
is one of the first intelligent things we sent out into the universe. And so they picked up on it and sent it back to us like, hey, we got your message, you know, like, this guy looks fun, you know, he's hosting a bunch of races, like, yeah, you know what I'm saying, like, so I mean, that's how the book goes, obviously, but that's like the rationalization is that, you know, that's one of the first, like, signals we sent out worldwide, so, you know, worldwide signals don't just go to us, they go everywhere, and so that's like, you know, our radio signals, our television signals and things like that, are radio communications between, like, satellites and Earth. Yeah, they get back and forth, but like when we send a radio signal up to the space station, it doesn't just go to the space station. Like it just goes out, and the space station picks up on it. yeah, it's on the right frequency, but that the other signal just keeps going.
So does that mean like if aliens are on the right frequency, like a long way away, they'll be able to hear it?
Yeah, yeah. If aliens are on the right frequency, a long, long way, yeah, they'll hear it. But they'll hear it 60 years from now.
Yeah.
You know, or however many light years they are away from us, because radio signals travel at the same speed as light does. It's electromagnetic radiation. So.
So if this like alien were to come at like say half the speed of light
Yep.
towards us,
Yeah.
would everything start going a lot faster?
Yeah, in essence.
Like it's,
They start picking up signals quicker and quicker and quicker. Right? So, we know now, we have evidence that light is affected by gravity, but we still don't know how. Tomorrow, we'll answer it.
Oh, yeah, let's do it.
We actually see soul limiters.